We're now going to take a look at some more identities. So we're going to start off with a set of sum and difference identities. And this lets us know what to do when we have a sum or difference inside of or for our argument for our cosine, sine, or tangent functions. So this is a reference. By no means do I want you to memorize this. You're going to just refer to it. The more you use it, you'll just get used to it, used to what they are. So notice that the cosine arguments, notice that it's always cosine of each angle in front minus the sine of each angle. And we're actually doing opposite of a sine. So there are some patterns there, but you don't have to memorize them. But whenever you're trying to find a cosine or a sine or tangent of a product or difference, we can actually convert that into like products. And this becomes a lot easier for us to use, or it makes it easier for us to simplify expressions that contain variables in that argument. The next set of identities we're just going to go over, and this is actually more of a reminder, a refresher. These are our cofunction identities. So whenever you happen to be taking a difference of two arguments, and one of those arguments, or that first argument, is pi halves, we don't have to use the full co-identity or the sum and difference identity. You'll get the same answer, but the first argument, like in a difference, is pi halves, so you can actually skip a lot of steps and go straight to these other functions. So if you had cosine of pi halves minus something else, you can rewrite that as sine of that something else of your theta, and so on and so forth. So this is something to keep in mind as we're solving our problems. And on the bottom, let me just hide this. I just have a right triangle, and that's just reminding us why this is true. So remember, in any right triangle, the sum of all, or any triangle, the sum of all of our angles is 180. However, in a right triangle, we already know one of those three angles is in 90 degrees. And that leaves us with just 90 degrees for the other two. So if one angle is theta, the other angle must be pi half minus theta. So we get that, the cosine of one is really just the sine of the other and vice versa. And we can get that same relationship for tangent. So now let's take a look at a couple of examples where we get to use these identities. I included in the example and on your work slide the unit circle, just as a quick reference, so you don't have to pick up that calculator. You can, if you would like. But a lot of times when we're working with these different identities, we're trying to make sure that we can get everything in terms of something that we can find on a unit circle. Doesn't always work out. So let's just take a look at example 4. And you would notice here that there's only one thing, only one argument, or one item in that argument. So we said we're using the sum and difference identity, so we have to change this into a sum or difference. Otherwise, you can just put this into your calculator. That will work too. But if we want to get an exact number without the calculator, we can rewrite this as a sum. And I'm going to strategically rewrite this as the sum of two things that I can easily find on the unit circle. So I know I can get 4, 6, and third. So I'm just going to rearrange this. So I'm going to say cosine. And I know 7 pi 12. I can rewrite that as 3 pi 12 plus 4 pi 12. And this is something you would have to play around with just to see if you can get that right combination. I did this before, so that's why I'm doing it very quickly. And again, these reduce, right? 3 over 12 is the same as 1/4. And I know this is a bit silly because we're working with whole numbers, but eventually, or we're working with all numbers, you can just put this into the calculator. But this is just more as an example because you see later we're going to start to use variables. So you can't just throw it into a calculator if you have variables. So this is just practice using a simple example and showing that you can break up anything into a sum if you want. Okay, so now I have my sum. I can then apply my formula. So I know that the cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta, right? And alpha and beta are my two arguments that I'm adding. So I can just substitute, that should be equals. So we have cosine of pi fourths times the cosine of pi thirds minus the sine of pi fourths minus, times the sine of pi thirds. And then I can use my unit circle to identify these numbers. So cosine of pi fourths, my pi fourths here. So the cosine, my x-coordinate, is square root of 2 over 2. So I'm going to write that over 2 times, and then my cosine of pi thirds, right here, 1/2, minus the sine of pi fourths here. So the y-coordinate is square root of 2 over 2 still, times the sine of pi thirds. So I'll go to pi thirds, my y-coordinate is square root of 3 over 2. Let me just make a little more space. I'm going to finish writing it over here. So I know I can multiply these through, so I'll get negative, actually, this was equals, right? It was not negative, equals square root of 2, and I multiply my denominators, like over 4, minus, and I can multiply the two things under the radical, so that would be square root of 6, 2 times 3 is 6, over 4. And I can decide to make them both over 4 like this. Since they're both over 4, I'll just stretch that line, and that will be my final answer. So it's not pretty, but if we want an exact answer, I would leave it right there. So now let's take a look at number 10. So here we have a variable, so we have no choice. We can't plug this into our calculator. But here we can use, and we have a sum already, so we have a sum inside of for our argument for sine function, so we can use that rule. So we know sine of alpha plus beta, right, is equal to, and I'm just referring to my notes, so that's equal to sine alpha cosine beta minus cosine alpha sine beta. And now I can just substitute the values that I have into this equation. So it's sine x cosine of 11. Oops, that should be 11. I'm starting to write pi. Cosine of 11 pi over 6 minus the cosine of x sine of 11. I keep doing that. I'll put the 11 in front. 11 pi over 6. So now I just can go to my unit circle to figure out what this value is. The cosine of 11 pi over 6 and the sine of 11 pi over 6. So I see it right here. So my cosine is square root 3 over 2. So I could just move that to the front. The sine of x I'm going to have to leave alone. I can't do anything about that. Or that's as simple as it gets. And then minus the sine of 11 pi over 6. That's 1/2. So 1/2. So we're going to move that to the front, and I'm going to put a cosine of x. And this is as simple as we can make it. Right there. The final question we're going to look at is number 14. So we have a cosecant of pi halves minus t. So a couple of things. I noticed that one, I have a co-function. It's a cosecant. I could rewrite that as sine instead, like 1 over sine. But I also noticed that the first number that's in my argument is a difference. And the first number in the argument or value is a pi halves. Now remember my co-function identities, right? So I don't have to go all the way through the trouble of using my sum and difference formulas when I have that. I can actually shortcut and go straight to the idea that whenever I have a cosecant of pi halves minus anything, any angle theta, that's actually equal to the secant of, in this case, t. If you want to prove it to yourself, you can use the sum and difference angles, but why do that when we don't have to? So we already know that this is something that we can quickly write. So there you have it. So what I want you to do now is I'm going to just clear this. So I want you to go on and do some on your own. You're going to do 5, 11, and 15. And just like the other set, you notice that these are underlined in blue. That means if you go to the OpenStax textbook to the answer key, you're going to find the answer. So I want you to try these on your own, check your answers, and then see how well you do.